Welcome to Cramer's rule. This is my favorite Cramer right here, but this is not the Cramer that the eponymous theorem is named after. The Cramer we're talking about was a Swiss mathematician, lived in the 1700s, highly regarded. So before we do Cramer's rule, let's just spend a page reviewing. So suppose we have a matrix A, and we want to find an elementary matrix such that EA is this matrix. And so how is this matrix related to the matrix A? It looks like -1 times row 3 was added to row 1. So in order to achieve that elementary row operation, the elementary matrix we would use is the identity matrix, where we do that same operation to the identity. So 1, 0, -1, 0, 1, 0, 0, 0, 1. And if you multiply E by A, you will get the same matrix. Okay, let's suppose that the determinant of the matrix ABCD is D. We want to find these two determinants. The first one's very simple. It's just a straight up swapping of two rows. So that's going to be minus D. That will introduce a minus sign. The next one, we need to go a little slower. First of all, if we want to get back to the original matrix ABCD, let's multiply row 1 by 3 and add it to row 2. That will not change the determinant. So this will be equal to A, B, 4C, 4D. Now we can pull a 4 out of row 2. A, B, whoops, there's a 4 there. A, B, C, D. And so we have 4D. Okay, if A is this matrix, find the determinant and find all values of P for which A is invertible. Now you recall that a matrix is invertible if the determinant is not 0. So what we're going to need is that the determinant of A is not 0. So the determinant of A, I could use straight up cofactor expansion right now, but I think it'll make my life a little bit easier. Let's do some row reductions first. Let's leave row 1 alone and use it to kill off this 3 and this 5. So I'm going to add -3 times row 1 to row 2 to get 0, P minus 3, P minus 3. That won't change the determinant because that's a row replacement operation. And then on the last row, let's multiply row 1 by -5 and add it to row 3, 0, 0. And then -5 plus 2 is -3. Sweet. Now I've got a triangular matrix. I can just multiply the entries on the main diagonal. -3 times P minus 3. So there's the determinant of A. And for invertibility, we need P not to be 3, because that will make the determinant 0 and A would not be invertible. Okay, now a few true false and one definition. A is invertible if and so you should just pause it and do these on your own. All right, hopefully you did that. A is n by n. A is invertible if and only if the determinant of A is 0. No, we just looked at that. Determinant A should not be 0. B, AX equals B has a unique, that's the exclamation point, unique solution for all B if and only if the determinant of A is not 0. That's true, that's the IMT. C is false. The determinant of A transpose is just the determinant of A. D is false. The determinant of A inverse is 1 over the determinant of A. E is true, and F is false. You can come up with two matrices A and B, easy examples where this is not a true statement. So you should think about, can you do that? Pick 2 by 2 matrices with a lot of zeros. Okay, finish the definition. Very important. Hopefully you know this by now. A set of vectors is linearly independent if the only, huge word there, only solution of the equation x1 v1, you could use c's too, you don't have to use x's, x1 v1 plus x2 v2 plus ... plus xp vp equals 0 is the trivial solution. x1 equals 0, x2 equals 0, ... xp equal 0. All right, so now Cramer's rule. Cramer's rule is a rule for solving a system ax equals b. It's not the way you want to solve a system in general, but it's good to know, and it can be used sometimes. All right, it requires finding a lot of determinants. That's why I'm saying it's not really your go-to method. First of all, we need some notation. A sub I of B, if A is a matrix, is the matrix you get by replacing the ith column of A by the vector B. So here's an example. I've got a linear system. A is the coefficient matrix. B is the answer column. A1 of B, I take the matrix A and I replace the first column with B. So 7, 1, and then I finish off A, negative 3, 5. A2 of B, I take the matrix A and I replace the second column with B. So straightforward. All right, and here's Cramer's rule. If you have an invertible n by n matrix, then the unique solution of Ax equals B is, here's a 2 by 2 solution and a 3 by 3 solution. This generalizes to 4 by 4, of course, but I won't give you any more than 3 by 3. The first coordinate of the answer vector is determinant of A1 of B over determinant of A, and the second coordinate is determinant A2 of B over determinant of A. So let's use this. Here we've got a linear system. A is the coefficient matrix. B is the answer vector. We're going to need determinant of A for both entries in the answer vector. So let's just find that right now. Determinant of A is 10 minus a negative 3, that's 19. Okay, so x is equal to, instead of x1, x2, I have xy. Determinant, I'm going to state my formula, determinant A1 of B over determinant A. Okay, so I stated the formula, now I'm going to use it. Determinant of A1 of B, we found A1 of B above. We take the matrix A and replace the first column with B. So 7, 1, negative 3, 5. That's the notation for determinant. And then below, I'm just going to put 19 because we found determinant A is 19. Okay, 35 plus 3 is 38 over 19. It goes in twice. Okay, and y, I'll write down the formula, determinant A2 of B over determinant A. Okay, A2 of B is the matrix A with the second column replaced by B. And put 19 in the denominator. All right, 2 minus 21 is negative 19 over 19, which is negative 1. So x, the vector x, which is xy, is 2, negative 1. There's my answer. Okay, here's a 3 by 3. I'm only going to do, so the answer is going to be x, y, z equals, I'm going to do the x, and for homework, you're going to do the y and the z. So at the end of these lecture notes, there's 2 practice problems. The first one is to finish solving the system. So I'm going to start you off, and then you're going to finish. Here we are. Okay, so I started us off, I wrote down the coefficient matrix A, I wrote down B, and I already found determinant of A is negative 2, just to save time. So I did that for us. And then X is going to be, I'm going to write down my formula, determinant A1 of B over determinant of A. Okay, now determinant A1 of B is going to be the determinant of a 3 by 3. So I'm going to take the matrix A and replace the first column with B. 1, 4, negative 3. And then the rest of A is 3, 2, negative 1, negative 1, negative 1, 1. Dividing by negative 2. Okay, so now I want a determinant of a 3 by 3. I'm going to do some row operations first to simplify before I use cofactor expansion. And you don't always zero in on the first column, like think, oh, I need to kill the 4 and the negative 3. If I want to keep the numbers small, and there are many ways to find this determinant, you don't have to do it my way, but what I'm going to do is focus in on this last column. I'm going to take this 1 and kill off the negative ones above by row replacement. So if I add row 3 to row 1, I get negative 2, 2, 0. And if I add row 3 to row 2, I get 1, 1, 0. And then just leave row 3 alone. Okay, now I'll do cofactor expansion on this last column. So this is equal to 1 times negative 1 to the 6 times the subdeterminant negative 2, 2, 1, 1. That's all over negative 2. Okay. And that's, well, this part's all just 1. So negative 2 minus 2 is negative 4 over negative 2. So I get 2 for the x coordinate. Okay. Here's an application, geometry of the determinant. If A is a 2 by 2 matrix, the area of the parallelogram spanned by the columns of A is the absolute value of the determinant of A. This was from section 3.1. And we did a problem like using this theorem. And I just want to show you it generalizes. If A is 3 by 3, the volume of the parallelepiped, that's just a three-dimensional parallelogram, spanned by the columns of A is also the absolute value of the determinant of A. And so here's a problem. Find the area of the parallelogram, and we're given 4 vertices. And I plotted those vertices to show you what the parallelogram looks like. In this case, we're not given vectors that span the parallelogram. Our job is to find those vectors. One way of doing it, it's not the only way, but one way of doing it is take this parallelogram and transfer it so that one vertex is at the origin. So translate it. The way to do that is to subtract one of the vertices from all the others. It doesn't matter which one. I decided to move this guy to the origin. That means I took all 4 vertices. Here's the start of the computation over here, all 4 vertices, and I subtracted that one vertex, 0, negative 2, from each one. So let's see what we get. First one goes to 0, 0. That was my goal. Okay, the second one goes to 6, positive 1. The third one goes to negative 3, and then 3. And the last one goes to 3, and then 4. And I plotted those 4 vertices over here, and you could see now my parallelogram looks the same, but it's been translated so that one vertex is at the origin. What that gives me is, if I call this vector u and this one v, I always take the 2, if I'm looking for 2 vectors that span a parallelogram and one vertex is at the origin, I always take the 2 vectors that start at the origin. Those are my spanning vectors. So I'm going to take u and v, and u is just the vector negative 3, 3, and v is the vector 6, 1. Now you could switch those labels. You could make u 6, 1 and V negative 3, 3. It wouldn't matter because you're going to take the absolute value of the determinant. And so you'll get the same answer in the end. So the area of the parallelogram is the absolute value of the determinant, of the matrix with U and V in as columns. So negative 3, 3, 6, 1. And I'm using absolute value there instead of double bars. Okay, and that's the absolute value of negative 3 minus 18 is negative 21, which is 21. And if you'd switched the labels U and V, you would have gotten absolute value of positive 21. You would also get 21. Okay, theorem 10, stronger version. So we've got theorem 9. Theorem 10 talks about how to find the area of a region after it's been after a linear transformation has been applied to that region. So if we have a linear transformation and it's got matrix A, S is any region with finite area, then the area of the new region T of S is the absolute value of determinant A times the area of S. Okay, so a super easy example is reflection about the y-axis. So I've drawn a parallelogram S. When I reflect it about the y-axis, its area isn't going to change. So T of S is over here. Now, what is the standard matrix A for reflection about the y-axis? So remember how to find that. You look at what this operation does to the standard unit vectors. So E1 goes over here. So it's got coordinates negative 1, 0. And E2 just sits there, doesn't go anywhere. So 0, 1. The determinant of A is negative 1. So the absolute value of the determinant of A is 1. So the area of T of S is just the area of S because this is 1. All right, let's look at another example where T actually does change the area. T is going to stretch the area out. So let S be the parallelogram spanned by B1 and B2. So I have a picture of S there. And T is a linear transformation with this standard matrix. That's the matrix A. All right, and B1 and B2 are the vectors that span that parallelogram. Find the area of S using theorem 9. All right, so by theorem 9, the area of S is equal to the absolute value of the determinant of the vectors that span that parallelogram, B1 and B2. So B1 is 4, negative 7. B2 is 0, 1. That's the absolute value of 4, which is 4. So there's the area of S. Find the area of T of S under the mapping X goes to A times X by using theorem 10. So theorem 10, I'll just remind you, says the area of the new region should be the area of the old region, which is 4, times the absolute value of the determinant of the standard matrix. So let's find the determinant of A. Well, let's find the absolute value of the determinant of A. That's absolute value of A is 7, 1, 2, 1. 7 minus 2 is 5. So there's an absolute value of 5, which is 5. So by theorem 10, area of T of S is 5 times the old area, which is 4, which is 20. All right, I'm going to verify this theorem in this case. So this is a long example, but what I'm doing is I found the area of T of S using the theorem, and now I'm going to find the area of T of S directly. So let's find T of S, see what it looks like. Here's a picture of it here. Verify that T takes B1 to this vector and B2 to this vector. So how would we do that? Well, we know the matrix for T. It's A. A is what? 7, 7, 1, 2, 1, those two columns. So T of B1 should be A times B1. So 7, 1, 2, 1 times B1, and B1 is, I've forgotten, 4, -7. Okay, so let's see, that's 28 minus 14, which is 14. And then 4 minus 7 is -3. Okay, so we verified that. T of B2 is A times B2. So 7, 1, 2, 1. B2 was, let's see, 0, 1. Okay, so that's 2, 1. Check. So here's T of B1. And this vector here is T of B2. And there's the new parallelogram. It looks a little bigger than the old parallelogram. Actually, it is. We know it is because the area of the new parallelogram is 20. The area of the old parallelogram was 4. All right, so find the area of T of S directly. So if we want to find the area directly, we just take the absolute value of the determinant of T of B1 and T of B2. So area of T of S is going to be the absolute value of the determinant of the spanning vectors, which are 14, -3, and 2, 1. Okay, and that's absolute value of 14 plus 6 is 20. Absolute value of 20 is 20. So we got the same answer. But we had to do a lot more work. So if you don't use the theorem, you actually have to find the new parallelogram and then use theorem 9. Theorem 10 allows you to avoid that. You just find the area of the old parallelogram, or whatever region it is, and then multiply by the absolute value of the determinant of the standard matrix. Okay, and that is it for this section. You got a couple of practice problems. You need to finish the system in example 2, and then I gave you one that's just like one of your homework problems. The answers built in show that the solution to this system using Cramer's rule, this system here, using Cramer's rule is this. So here's the answer, and you're going to use Cramer's rule. All right, and that is the end.